Hello, this is Miraj Patel, and today we're going to be wrapping up Unit 12, and we're going to wrap it up by talking about equilibrium of solutions and all sorts of stuff. And because this is a very short topic, I was just planning on reviewing everything. So at the end of the video, we'll just go back to some previous PowerPoints that we've talked about this unit and briefly review. And so without further ado, we're going to talk about equilibrium. And so, in football and other team sports, we always have the same number of players on the field. And I'm sure most of you know that. And so, even though we have the same number of players like this, the players can enter and leave, but the same total stays on the field. So, I think here we have like 10 players. And so, even though there always has to be 10 players, they can switch out and in, and this all has to do with because we take in one and or we put in one and we take out one. So the rates are always the same. So if for every one we take out, we put one back in, so it's the same. Otherwise, it would be a dumb idea to play with 9 players when you can play with 10. And so this all has to do with this equilibrium, and this is so similar to chemistry. And equilibrium is when two opposing processes occur at the same rates to achieve a balance. So just like in football, we take out one player, we put in one player. So this is technically equilibrium because the opposing processes taking out a player and putting in a player happen at the same rate. So it's equal here. And so let's just say we have club equilibrium, and so we can have 200 people here maximum. And then we have VIP here. And so VIP, there can only be 20 people in VIP. So when the club opens, we have 200 people, let's just say spontaneously, bam, like that. 200 people get into this blue area. And right now we have 0 VIP. So this is the beginning of the club. And so as the club begins, let's just say anyone can get into VIP. So let's just say there's a lot of people here that can go into VIP. And so in the first like maybe 10 minutes, VIP opens, and then 20 people just jump in right now because it's empty. So let's just say 20 people went in. So this 200, we lost 20 people because they went to VIP. And so there's 180 people in this club right now outside in the non-VIP, and then there's 20 in VIP. And you know how people are. People are, always on the move, especially when they're partying. And so let's just say, people always leave and go. So people can leave and enter VIP. And so let's just say some people left. And when people leave, some people can replace them. So in VIP, there's always 20 people because there's people always waiting to get in and there's people always going out. So this is why, because the rate of going in and out are exactly the same, so going into the VIP and going out of VIP are the same, the number of people in the club and in VIP stay the same. Notice how on this graph it's constant. And this is called con-con-requal because and I'll explain just in a minute. So con-con-requal means that the concentrations are constant, hence the con-con, and then rates are equal because look at this. The rate going in, so like to say one person goes in, the rate going out are the same. So notice here, the rate going in, so one person comes in, and the rate going out, one person leaves, are equal. So because of the balance, there's always the same number of people, but they can always change because people are still moving around. So this is con-con-requal. And it's always important to know that the concentrations are constant, not equal, but the rates are equal, which sort of make the concentration constant, even though it's called equilibrium. So just get this straight. So concentrations, or the number of people or molecules, whatever you want to think about, are constant, but the rates are equal. So hence this constant area. And so here we have all sorts of equilibrium. So here we have phase change equilibrium. And so we have water molecules. And since we learned this, we've learned that rates are equal. And even though when water, it doesn't look like it's evaporating, there is always some water leaving, some water condensing and evaporating all the time. And because these rates are equal, the concentration of the water in the air, the water vapor, is the same as the water in liquid form. And so it looks equal, but we always know that there's always something going on. Even in chemical reactions, there's always some reacting going to products or reactants and back and forth. But because they're happening at equal rates, it looks like nothing's changed, but we know that there's something going on. And this is an example of con-con equal also. And so here we have another one, but this involves saturated solutions, which we talked about earlier this unit. And so saturated solutions are solutions where there's still some crystals, there's like maximum number of a solvent in this, solute in the solvent. And so we have some little leftovers that don't dissolve. And so in this little crystal here at the bottom, some still dissolve, so we have solvation happening, and there's some crystals forming all the time, even though the total of this huge crystal does not change. So here's a diagram. Notice how one comes in, one leaves. One yellow leaves, one yellow comes in. One green leaves, one green comes in. One yellow comes in, one yellow leaves. So notice how for everyone that comes in, one leaves. And so this is exactly what I mean by the rates are equal. So for every one thing that leaves, something replaces it. And so the total crystal does not change, but the molecules that make it up change because they're always replacing each other. And so this all has to do because the rates are equal, the total molecules of dissolved remain constant, and the total molecules of undissolved also remains constant. This is again con equal. And so moving on, so here we have one last example, and so this is an example of a chemical reaction, and now we're going to look at a chart instead. And so these are two charts, and this one shows time at the bottom on the x-axis, both of them do, and then this one shows concentration on the y, this one shows rate. And so here we have the rates of, this is the reactants, and then at the bottom is the products, right here, products and reactants. And so notice at the beginning, the reactants, there's almost 100% or a lot of reactants. And then at the very beginning, there's 0 products, this red line. There's 0 at the beginning. But then as we start time, the reactants move down because they start reacting. And when we know that they react, they form a product. So as this one goes down, as reactants go down, products form, and so the concentration of products increases. And then in this line graph, as reactants react, and the products form, they meet at this one point here, and after that point, both line graphs show that they stay constant. So, or at this one, they happen to be equal and constant, and then this one, the concentration just stay constant. And so once this straight line area is when they reached equilibrium. So once they started straightening out their lines, like right about here and here, they're at equilibrium. And so in this one shows rates. So we know that rate going in and out, or rates from reactants to products and products to reactants, are equal. So because those are equal, there's always something replacing another. The concentrations of the products and reactants are the same and stay constant. And so this is called also, Con-Con-Rico is also called dynamic equilibrium because there's stuff always going on, but the concentration in products and reactants remain constant. And also, it's important to know that they're not equal. The concentrations are not equal. If they were equal, they would be on the same exact line, but they're not. The rates are equal. So if we have a rate that's equal, that means they're changing the same rate. So there's one product forming for every um, reactant turning to product, and there's one product turning to reactant. So because they're always replacing each other, they don't change. That's why they're constant. They're not equal. The concentrations are never equal. Look at these two lines. They're not the same, but the rates are the same here. And dynamic just means that something's happening, and then equilibrium means that they're constant, and then the rates are equal. And so here's a quick quiz to see what you learned. When reactions have reached equilibrium, reactants and products A have stopped reacting, B continue forming, C have equal concentrations, or D decrease in concentration. So once we reach equilibrium, reactants and products we know are still forming, and and we know this because the rates just happen to be equal. So they have they stay constant, and because they're replacing each other, it looks like nothing's forming or being used up, but they do. And because they keep replacing each other at a constant rate, um, they um, they look like they're not, but they are. And this is called dynamic equilibrium when they continue forming, and because they happen at an equal rate. So for every one product used up, there's uh, one reactant that's reacting into a product. So it looks constant, and this is because there's still reaction happening, but they happen at the same rate. So this is question 2, and so a reaction starts with 100 molecules of reactants. So A is the reactants, and no product, so hence B is 0. As it approaches equilibrium, the forward rate will blank and the reverse rate will blank. So we have 100 of products. I mean reactants, sorry, reactants. And so as we want to reach equilibrium, they have to remain constant. And so once we start a reaction, just think about it. What happens to the reactants? Are they used up, or do they become constant, or do we get more of them? And in your head, you should be thinking, oh, they should be being used up. So when something starts reacting, the reactants are used up, hence the word reaction, because it's the reacting of the reactants. And so, yep, you are right when you say that they do react. And so if we react something in a chemical reaction, they turn into products. So as A starts reacting, there's more of B. And let's just look at the chart as a visual. So here we have the rate of reactants and products here. And so as we start, once we're at 0, 0, there's a lot of reactants and 0 products. So notice how reactants goes down because as we start reacting, at first it's very high, but then we lower the rate. And then it's the opposite for the the products. The products start reacting into the reactants because first you have to form products, so the rate is slow, but then as we get farther in, the rate from products, which are right here, increases because see how it increases. So the reactants, their rates decrease, and products, their rates increase. So those are the correct answers. And so which one says that? So the forward rate, so reactants to products will decrease. So we're down to B and D, and the reverse rate, so from B to A, will increase. So just remember that graph in your head, and so just remember how if we start out with a lot of reactants and no products, the rate of reactants has to go down. So there's some products, and then the products rate will increase. And so at this, okay, a reaction starts with 100 molecules of reactant and zero and no product. At equilibrium, the amount of product B here will be greater than A, less than A, equal to A, or constant. And so remember, we're just talking con or equal, or dynamic equilibrium. And we know at dynamic equilibrium or con or equal that the concentrations are constant. And we don't know exactly where these two concentrations will compare, but we always know that they're equal, or constant. Constant, I mean, because the rates are equal. So if we have one replacing the other all the time, that means they will always stay the same. So just think about a football game. We always have one player replace a player leaving the field. And so because the rate are equal, we have 10 players on the field and I don't know, maybe 30 players on the side. So those two concentrations are definitely not equal, but the rates are equal and that keeps them balanced. So at equilibrium, the rates are only constant. We do not know whether the products, there'll be more product or more reactant, or whether they'll be equal. We just know that they'll be constant. So just remember, at equilibrium, the concentrations are constant and the rates are equal. So just know those two things. And so now that we're done with talking about equilibrium, we're going to go quickly and review solutions. So if you don't want to review, you can stop the video and tune out here. But now we're just going to be reviewing some basic stuff about solutions and stuff that we already talked about. So solutions are homogeneous mixtures, and remember, solutes are the substance being dissolved, and solvents are the medium that's dissolving the thing, so the dissolver. And remember, solvent is big, and so it sounds like a monster. And then solute sounds like a little and cute. So solute is present in a smaller amount, and then solvent is present in a greater amount. Solvent, and then little solute. So the solvent little monster eats up the little cute solute. So, or you can think about it as there's less letters in solute, so remember that's in smaller amount. Then we have types of solutions. I just know that there's all sorts of solutions, solids and solids, liquids and liquids, gases and gases, so just know that. And the reason why stuff dissolves is because we have IMFs between solute and solvent by themselves. And so these break, and so they pretty much form friends. So the solute and solvent have to like each other and form these little connections. So imagine them just like uh, two little friend circles, and then they intertwine. So they break their own connections and they form a nice, huge like friend circle instead of just two separate groups. And remember, if it likes to form solute solvent IMAFs, the greater solubility. And remember, electrolytes are just pretty much solutions that form ions and they conduct electricity, and most of them are ionic bonds. So think of nonmetals and metals ionically bonded together. Non-electrolytes are like covalently bonded molecules, like sugar, which is CH and O, which are all non-metals, so that means they're not ionic. But this one ionic because sodium and chlorine is a salt, and sodium chloride is just your basic salt. So it's ionic compound, so it ionizes and conducts electricity very well. Then we have solubility, and solubility is the ability or a maximum mass level of solute that will dissolve in a given amount of solvent. So pretty much how much can we dissolve at a given temperature and given amount of solvent. And so we have different solubilities for different substances and different grams amounts. And so remember the three types of solutions. Unsaturated is less than maximum dissolved. Saturated is at the level, the maximum dissolved, and hence because it's at the maximum, there's a little bit of crystals just to tell you that it's saturated, and then super saturated is more than maximum. So this is like going over limit. So this is like an elevator about to fall. This is an elevator at maximum capacity, and then this is an elevator that still has a lot of room for more things. So this is an example of unsaturated, hence no crystals. Notice that there's no crystals. Then this one's saturated because there's some crystals forming. And then this one's super saturated. Look at how many crystals there are. You can't even really see the solvent. And then polarity is important when we're talking about solutions. So remember, the same like dissolves like. So polar dissolves polar, and nonpolar dissolves nonpolar. So nonpolar is all by itself. And remember, polar can also dissolve with ionic because they both have charges. So it should be polar dissolves with ionic slash polar. So because they both have those little dipoles and charges on their molecules. But remember, nonpolar can't dissolve with polar or ionic, but polar and ionic can dissolve with each other. So remember, like dissolves like. And so this is an example of things that don't dissolve because they have different charges. So this one's nonpolar, this one's nonpolar, and water's polar, so it separates these two. So if we had just those C6H14 and C carbon tetrachloride by themselves, they could dissolve, but water's separating them. And so again, just remember, polar dissolves polar, and polar and nonpolar don't dissolve. So like because this is dissolving in water, we know that this substance must be polar, and then because this is not dissolving in water, we know that most people know that oil doesn't dissolve in water, and we know that because oil is nonpolar and water is polar, so they don't dissolve in each other. And then we remember the solubility curves, and remember, just read it by going on the x-axis and looking at temperature, and for a particular substance you just go up to the line and read that how much it can dissolve on the y-axis. And so if you need help reading and you want to reading these solubility curves, go back to the first video on unit 12, which had included solubility curves. And so remember, rates of dissolving, if something's warmer water and we're dissolving solids, it dissolves faster. Remember, if we have more surface area, or if we crush it up into smaller particles like this, we have more surface area, so there's more collisions and dissolves faster. Then if we have more stirring or agitation, because we're moving around the solute, it hits the water more or solvent more often and dissolves faster. And then higher temperature also causes dissolving of solids faster. Then gases are weird, and so gases dissolve with no stirring and high pressure and low temperature. And no stirring is because if we stir it up, gas gets energized and it can leave. High pressure because we need to squish the gas into the liquid, and low temperature because gas has a lot of high energy. So if we lower the temperature, less energy, so the gas particles will stay longer in the liquid. So just think about sodas when you're thinking about gas dissolving. So pretty much we don't want this to happen. This is caused by when you shake up soda bottle, which causes the gas to get out, and hence that's why all this Coke leaves, because all this gas is escaping. So just think about soda bottles and where we keep them and relate it to dissolving. And so now we have a next PowerPoint, which is going to quickly go over molarity. And so remember, concentration is the relative amount of solute dissolved per given amount of solvent. So we have four test tubes, and we have different amount of solute and solvent, and because of these changes, we only have 4 solute per 8. So the formula for concentration is solute over solvent, and it'll always be like that. So we have 4 per 8 hashes of water, so this is a concentration of 1/2. And this is very dilute. And then on this side, we have 8 solute molecules per 4 water hashes. So it's very concentrated. This one has a concentration of 2. that one has 1/2, and then these two happen to be equal because they have one solute molecule for every little water hash. And even remember, solute is a ratio, so even though a solution has way more water in solute, they have the same exact concentration because they have the same ratio of solute to solvent. So this is the comparison between each other. So these two are equal. This one is less concentrated than this one, and then this one is most concentrated. Then we have molarity, which is a measure of moles of solute per liter of solution. And so that's the formula, and so all you have to do is know that it's moles over liter, and it's usually 1 liter most of the time. And there's 3 ways to write it, and so don't get too caught up in how to write it, but just know that all these mean the same exact thing. And so, so when you're doing these problems, just make sure when you're doing the fractions, you just use the same rules like we all been talking, that we have moles on the top, and so because we have moles on the top, we put moles on the bottom of the next fraction, and so it cancels out. And whenever you have molarity, always remember 1 liter is with the moles. And so so here we have moles will cancel out, and we'll just be left with liters, which we need to find, which is volume. And so if you want to see the calculations, just go back to the video, the second video in this unit. And so now we're going to quickly review dilutions. And so remember, dilutions are when we lower concentration or molarity by adding more water. So notice how there's twice the number of water in this one as in this beaker here. And so because we added more water, we increase the denominator here, and we decrease the number of molarity. And so here we have the equation for dilution. So pretty much it's molarity of initial molarity times initial volume is equal to molarity of dilute solution times volume of dilute solution. So just remember to plug these all in, and remember to sort out what's in the problem. And then once you figure out where everything is, plug them in the equation. And pretty much to isolate the variable, we divide by what's next to it. So in this case, we divide by 2, the other side, both sides by 2, and that's how we just get our answer. So just remember, just isolate the variable by dividing. And so now we're gonna finish up by talking about solution stoichiometry very briefly. And so I just want to show you that what we've learned in stoichiometry, and remember how to do the conversion. So we have moles, and moles are 6.02 times 10 to the 23rd atoms of or molecules of a substance. And so for moles, we can go to grams, and we've already learned that in stoichiometry, in plain old stoichiometry. So remember using the periodic table and using molar mass, which is grams per mole, and then we have now we learned molarity, which is pretty new earlier this unit, and it's liters per mole, or moles per liter. And so this is the formula. And remember, in molar mass, there's always 1 mole per X amount of grams, which you get from the periodic table. For molarity, there's always 1 liter and X amount of moles, which we get from the problem. And so we have these two, which is all good. And then we have the same thing for substance B. And so we learn molar mass and then molarity, same thing. But remember, now we're going to remember how to convert from moles of A to moles of B. When we have a chemical equation, we can use mole to mole ratios. And remember that from stoichiometry, that we use these coefficients here to compare moles of A to anything else in this equation. So we could convert from A to B, A to C, A to D, just from using mole to mole ratios. And with these different pieces, so molarity, molar mass, and molarity of B, we can figure out from liters to grams of B. And so just remember to use this as sort of a visual, as sort of like a map to tell where you want to go. So let's just say if we start out with grams of A, we can convert to moles using molar mass. So we, divide by grams because grams we want them to cancel out. So we invert this fraction. And then we get to moles. From moles, you can pretty much go anywhere. So once you reach moles, you're like home free because from moles you can go to grams of A, liters of A, or you can go from moles of A to moles of B using mole to mole ratio. And then once you're at moles of B, you can convert to either grams or liters depending on you want to use molar mass or molarity. So always remember to, when you're doing these problems, sort out what you have and what you need, and always remember how to use these conversions. Whatever's on the top of the first fraction goes on the bottom so you can cancel out. And remember, mole to mole ratios are from the coefficients. Molar mass always has 1 mole for X amount of grams. The grams are calculated from the periodic table depending on which substance it is. Molarity always has 1 liter, and the moles are always given. Molarities always will be given in the problem, and it always changes. And so mole to mole ratios are from coefficients, and just always know that. And so just always know your basic rules for converting. And so that is it for the solutions unit. And then the next unit is going to be all about acids and bases. And so that is going to be our second to last unit. So yippee, you got this far in chemistry. So we're not that far to go until we reach our last unit. And then our last unit is going to be gases and gas laws. And so we're going to be talking about gases, and next unit is going to be acids and bases. So until next time, I hope you have a good day, and I hope this really helped you review about solutions. And just if you want a more detailed review, I'm sorry, I had to go briefly to save time. Go back to the corresponding videos on this unit. And so so I'll see you later, and I hope you have a good day.